Basically, Octave can be used like a calculator. It's similar like a scientific calculator. The important mathematical functions like trigonometric functions, exponential function, logarithm and square root are already built into Octave. For example, if I write sine of 3, it will calculate the sine function at the point 3. Likewise, if I write arccos of 0.5, it will give me the inverse of the cosine function at this point. With exp I can get the exponential function, so exp of 2.5 will be e to the power of 2.5. The logarithm is the inverse of the exponential function, so logarithm of this should be 2.5. With this command I can calculate the square root of the number. For example, the square root of 9 is 3. No surprise here. But what happens if I calculate the square root of a negative number? Well, I do not get an error message, but 0 plus 2i, because MATLAB and Octave knows how to handle complex numbers. All of these built-in functions operate also on arrays, so if I write sine of 2, 3, 5, it will be... I might wonder, well, what this is not defined. Sine only works on numbers and not on vectors, but if I hit enter, it will calculate the sine function on each element. For example, sine of 2 is 0.91 and sine of 3 is 0.14. So what it does now, it calculates this function on each element. Likewise, if I write exp of 2, 3, 5, I get e to the power of x for each element. As I mentioned before, vectors can be defined by using brackets. For example, u equals to 2, 3, 5 will give me a three-dimensional row vector or a 1×3 matrix with these entries. If I use semicolons instead of commas, for example, 1 semicolon minus 1 semicolon 0 will give me a column vector or a 3×1 matrix. I can also see that by using the size command. Size of u is a 1×3 matrix and size of v is a 3×1 matrix. To define matrices, I can combine this notation of using commas and semicolons. For example, if I want to get a 3×3 matrix, I can say A is brackets 2, 7, 2 semicolon to get the next line, the next row, 3, 1, 4, and then semicolon 42, 73, let's say 100. Now I have a 3×3 matrix with these elements. To access data in an array, so to access data in a vector or matrix, I can use normal parentheses. For example, if I write u of 3, I will get 5 because 5 is the third element of my vector u. The first element would be the 2, the second 3, and the third entry is the 5. Likewise, for the matrix, I can write A of 1, 2 is 7, because this is the element at the first row and the second column. Instead of just reading this data, I can also write it. For example, writing A of 3, 2 can be changed to, let's say, -5. Then it would change the data at entry 3, position 3, 2 to -5. As you see, this is the only entry which changed, everything else stays the same. Sometimes it is very useful not only to access data at a specific point, but to access data in a complete row or a complete column. To do that, we can use dots. For example, if I write A of dots, comma 2, this will give me the second column. As you see, the output of this command is the second column of my matrix. Likewise, if I write A of 3, dots, this will give me the third row. This is the last row of my matrix. Of course, I can also change the data of a column or row. For example, if I write A of dots, 1, so I change the first column, and the data is supposed to be, let's say, 100 times A of dots, 2. So what it does now, it reads the data at the second column, multiplies it with 100, and then writes the result at the first column. So as we would expect, 7 times 100 is 700, and so on. So here we have the first column changed, which is 100 times the second column. There is also, as Octave is a mathematical software, it is no surprise that mathematical functions like matrix multiplication and dot product are already built in. For example, if I have this matrix A and the vector V, I can multiply this by writing A times V, and now it does matrix vector multiplication. But one might wonder, why is this useful that we can operate on complete rows or on complete columns? Well, this array could be a mathematical matrix, but we can also think of these array as data. For example, if I have real-world data from the medical field, from some patients, or from a physical experiment, which is then saved in an Excel table or a CSV table, I could read this into Octave and then do some calculations. Then it might be very useful. Let's give an example. Obviously, I do not have some real medical data, so let's construct some artificial ones. With the command run, I can get some random numbers which are uniformly distributed between 0 and 1. So, example, run 3, 2 will give me a 3 by 2 matrix where all entries are random numbers between 0 and 1. If I, instead of uniformly distributed random numbers, want to obtain normal distributed random numbers, I can write run n. Now I get normal distributed random numbers with expectation value of mu equals to 0 and standard deviation of sigma equals to 1. So let's say I have some patients, 20 persons, and they all have some ID. Let's say patient, and from 1 to 20. This is the patient ID. And all of them have a weight. I will construct some artificial data with expectation value 70 and standard deviation of 10. So this is supposed to be the weight of the patients between 53 and 81. And I will do the same for the height and for the age. Now I can combine everything to a data table by writing data as patient, weight, height, age. Now I have this table where the first column is the patient ID, the second column is the weight, the third one the height, and the last one is the age. Now this looks a bit complicated. I only want to display 2 or 3 significant digits. This is too long for me, so I just write format short G. And now if I display this data again, it's a bit shorter, a bit nicer. Note that this data, which is artificially constructed from random numbers, would be normally loaded from an Excel table or a CSV table from real-world data. So I want to get some insights into my data. For example, I could compute the average by writing the command mean data. This will compute the mean value for each column. So the average age is 55 or 54 years old, the average weight is 66.7 and so on. So with one command, with one operation, I get very interesting results without using complicated iterations, for loops or whatever. It's just one simple command. But let's say I want to get some more information out of this data. For example, let's say I want to know if the patients are overweight or underweight or not. To do so, we could use the BMI, which is constructed with the formula weight divided by height squared. If I hit enter now, I will get an error message which says for x to the power of y, only square matrix arguments are permitted. What does this mean? What does it say this to me? Well, if I define a square matrix, for example 1, 1 and 0, let's say minus 2, like this, I can calculate a to the power of 2, and this is the same thing as a times a. Likewise, if I compute a to the power of 3, this is the same as a times a times a. So this power symbol operates on matrices and is the same as matrix multiplication. So of course it only works on square matrices. But I do not have square matrices here, I have a vector of weight and height. So of course it will give me this error message. But obviously that's not what I want. I do not want to calculate this formula on square matrices, but I want to have it element-wise. For example, if I have the first patient, I want to calculate 77 kilogram divided by 1.74 meters, and then for the second, 52 divided by 1.75, and so on. So I have to calculate it for each row or for each patient element-wise. Fortunately, our error message also tells us how to do that. Use dot and then this power symbol for element-wise power. So anytime I want to make an element-wise computation, I have to use a dot before the operation symbol. So I write dot and then the division to have element-wise division, and then dot and then the power symbol to have element-wise power. Now it will calculate the BMI element-wise, and I will get the result which I want. So this is very useful because I can calculate new information, new data, like in this example the BMI, with just one single command instead of iterating over the matrix or over the array of data. So it's very useful because it makes it simple. Yeah, then there are, what else should I mention? There are some special matrices which are often used. For example, the command zeros 3, 2 will give me a 3 by 2 matrix where each element is 0. Likewise, if I write ones of 5, 3, I will get a matrix with 5 rows and 3 columns where each element is 1. I could multiply this with 42 and now everything is 42. To get the identity matrix, I can use the command I, which is a bit peculiar, but it is how it is. If I write I of 3, I get the identity matrix which is a diagonal matrix which has ones on the diagonal and zeros everywhere else. So if I write I of 4, I get the 4 by 4 identity matrix. Then there are some special vectors which are important to mention, for example the range, which basically works like this: start, dots, stop, dots, and then end. For example, if I write 0.2.10, I will get a vector from 0 to 10 with a step size of 2. So 2 plus 2 plus 2 and so on. Likewise, if I write 0.1.0.8, I will get a vector from 0 to 0.8 with a step size of 0.1. Instead of giving the step size, it might be also very useful to specify the number of elements which I want to have. I can do that with the command linspace. For example, if I write linspace 0, 0.8 and then 9 elements, I will get the exact same vector as before, from 0 to 0.8, but instead of giving the step size, I now said that I want to have 9 elements. Likewise, if I say linspace of 0 to 10 and I want to have 6 elements, I get the vector of before. This is very useful for plotting later. For example, if I want to define the range for the sine function, which has a wavelength of 2 pi, I could do so by writing x is equal to linspace, then from 0 to 2 pi, and I want to have 100 elements. If I hit enter, I will get a vector with 100 elements from 0 to 6.283, which is exactly 2 pi. Now the output is very long and complicated. Obviously this is too much for me, so normally what I would do is write a semicolon at the end, which will suppress the output. Everything else will be the exact same. I just don't see the output. What else is there to mention? Yes, it is impossible to combine the range with the fancy indexing from before. For example, we had 0 to 10, and we had data, and I can access, for example, the 8th row by writing this. This is nothing new, I explained this. But I can also say data of 2 to 20 and then dots, and this will give me each row where the index is even, because it starts at 2, has a step size of 2, and then stops at 20. So I get the second, the fourth, the sixth, and so on, these rows. Likewise, if I write, if this is data and I write data of with a step size of 3, I will get each third entry, for example 2, 5, 8, so each third row. So as you see, with these commands it is very easily possible to access and manipulate data within Octave.